Hello and welcome to our Wednesday webinar from the International Centre for Sustainable Carbon. My name is Benedicta and I'm part of the communications team here. Our monthly webinars are based on our technical reports, which are available from our website, sustainable-carbon.org. Residents of member countries and employees of sponsoring organizations can download our reports at no charge after a one-off registration on the website. Please type any questions you might have in the questions box as we go along, and we'll answer them at the end of the webinar. The subject for today's webinar is treatment of coal fines, presented by Graham Chapman and Peter Hand. Over to you, Graham.
Thanks, Benedicta, and welcome to everybody. I'll start the presentation off, and Peter will discuss some of the more technical aspects of treating fine coal. Excuse me. I'm in the UK. I'm not sure where everybody else is in the world, but I'm in the UK. Peter's in South Africa, so if we do occasionally try and say the same thing at the same time, then please bear with us. But just moving on to the start of the presentation. The issue today is really how do we treat and what are the environmental implications of fine coal, which is generally defined as being less than 1 millimeter in size. There are different definitions in different parts of the world, so we're not trying to get too hung up on the specifics there. But the main principle that we're here is that for coal processing, it almost always utilizes a gravity process. In other words, separating good, lighter product from heavier, less satisfactory product using a gravity system. And fine coal, and both of up to about 150 microns, and ultrafine particles, usually defined as being less than 150 microns, is not easy to separate in this gravity type process. And so it tends to create the problem that is often separated out and not treated and dumped in either surface or underground storage facilities, which create a lot of environmental problems, and of course means that the economics of the coal mining process and the coal production process are less attractive. So what we'll do today is we'll walk through the systems of how we treat coal, what the implications are for the treatment of fine coal, and perhaps some of the an overview of what different countries and different companies are trying to do to alleviate the problem, which has resulted in the storage, mainly on surface around the world, of very significant tonnages of the product of the fine coal. So the challenges with it, with fine coal, tend to revolve around the fact that it's not a particularly easy process to deal with, that the small particle size means that the coal tends to attract more water, more moisture, which is clearly not a good thing when you're dealing with a product whereby when the moisture will detract from its utilization process. And it's quite a difficult skill to actually design and treat systems which will actually produce material that is acceptable into the marketplace from a fine and ultra-fine coal. And Peter particularly has had quite a lot of first-hand experience of designing and operating systems like that. And so finally, we have both a situation whereby there's an economic opportunity, because clearly if you can produce 10 or 15% more material than you are traditionally doing from essentially the same process, that's only good news. And it also, of course, is an environmental issue, as we'll touch on as we go through this presentation. Where does fine coal come from, and why is it an issue? Well, I'm sure most of you are aware that the traditional black coal, the thermal coal and coking coal, is often called hard coal, and it is hard. It's called hard coal because it is hard. There's no great rocket science there. And if you've ever sort of, had an occasion to hit a large piece of coal with a hammer, you'll see it shatter usually into a significant number of pieces of all different sort of shapes and sizes. And during the mining process, you have to effectively either in the opencast scenario blast the coal with explosives. This is usually conducted and planned in quite a careful way, so that you minimize the use of explosives to reduce costs, but also you try and avoid the creation of as much fine coal as you possibly can. But it still has to be blasted to be mined, and then it goes through the crushing systems to allow it to be handled and processed. In underground mines, you normally transport the coal to surface from using a series of conveyors, and as each particle is carried through the system and goes through different chutes and transfer points, again, breakages occur and fine coal is created. And then finally, before the coal is usually treated in a coal beneficiation plant, it's usually crushed through -50 millimeters to allow the treatment to the processing to occur, and that in itself creates a fine coal material. And then finally, after all that, you finish up usually stockpiling it, loading into trains quite often, or maybe onto conveying systems, and then quite often into ships. And all of this creates a situation whereby you produce a fine material. In very rough terms, that's usually between 10 and 20% of the total product, of the total amount of coal used. It does vary quite significantly, and we'll discuss that in a little bit more detail later on. But I think it's from the experience that Peter and I have had in working in virtually all of the main coal-producing countries, that will be a fairly reasonable figure to understand as to what we're actually creating here. And so, what's the problem with that? In the sense that most people, when coal is being used, actually use it in a fine form. It's pulverized quite often in most power stations to a relatively fine size and then blown into the boiler. So, you know, if you're getting your coal already at least partially pulverized, isn't that a good thing? But there are two real problems with it. One is that the larger surface area means that you tend to attract moisture into the product, and moisture detracts from the heat available in the boiler, and therefore reduces the overall efficiency of the process, which is never a good thing. And secondly, is that high moisture content also, and the fine particle size, means it's quite easy for the fine coal, especially high moisture fine coal, to stick in transfer chutes and various transfer points as it's taken to its final point of usage, all of which again reduces efficiency and causes problems. And of course, fine particles are more likely to come airborne. There are situations where, especially in some indoor environments, where it can become an explosive mix, and as a very fine product, it can also leak into water systems and cause environmental problems that we'll discuss in a little bit more detail later on. So it does represent a problem. It's very difficult for most customers to deal with fines, and a lot of coal contracts will have a specific number in there which limits the amount of fine material that can be included in the overall product. And so wherever possible, it's best to avoid it. So I'll hand over to Peter now, who'll just take you through a quick summary of how we normally produce or process, coal, and how we deal with fine coal as a more of a specific product. Peter?
Okay, thanks very much, Graham. First off, my apologies. I'm just getting over a bit of an illness, so my voice is not too great, and so my apologies up front. Okay, the slide we have up is basically showing some of the based on the size of particle, what sort of coal processing options we can have. On really there are two different types of jigs, I guess. I mean, jigs have been used down to about 1 millimeter and often in the same machine, but you have a problem where a jig is basically a water-only device, and as you stratify the bed, you have both size and density effects. So a ROM jig is really used on nominally the plus 20 millimeters. The efficient processes are the dense medium processes, where you have a mixture of magnetite in water to create a pseudo heavy liquid, which you can control to a specific SG to give you the product quality that you need, and you can be fairly precise, and the efficiency is very good. Now, baths that tend to be used Certainly not lower than 6 millimeters, but 10 mm and above fairly commonly. There is a tendency for more and more coal to be treated in dense medium cyclones, which also uses dense medium, but also adds a centripetal force onto the particles to accelerate the separation between light and heavy materials. That in itself does have a problem sometimes, where if you are using a dense medium cyclone, often people will decrease the top size purely because you have to have, there is a limit on the top size entering a cyclone. That in itself means you actually crush more. So let's say you need to get it down to -50, but you could actually treat it -100. You are increasing the amount of crushing you have there, which on its own actually increases the amount of fines, which means you have more fine material to treat in a separate process. At the bottom three pieces of equipment there, there are other pieces of equipment which we will be going into just now, but spirals have been very, very common worldwide. They are not inherently very controllable. You can't really drop the density down. So let's say to produce something like a 27 or a 28 CV cut type coal, you need to get below, call it a 1.6 density. It's actually very, very difficult to do that. So that's one of the problems with the spirals. Below that, we have a teetered bed, which is really a hinderless settling device. All of these problems, once again, these are water only. So they actually take more time to actually separate. They're not inherently as efficient, and you also, same as with jigs, you get that effect of size and density. So a very small particle will probably go with a very light material, so that it could be fine discard material is actually going out with your coal. And then at the bottom there, we'll talk a little bit more about this, is froth flotation. Froth flotation, as in mineral circuits, nominally -0.5 millimeter. Depends on your location in the world. For example, in South Africa, it's actually very, very difficult to use froth flotation on plus, call it 200 microns, but obviously test work will tell you what's going on with that. Okay, can we have the next slide, please, Graham? Graham?
Oh, yes, it's come up.
So, yeah, there we go. So, okay, this an interesting sort of slide, which is really how technology has developed over a period of time. So, jigs have been used for a very, very long period of time. And also things like barrel washers. Barrel washers are still in use. They're effectively a sluice. You're putting water down a barrel. The lighter material picks up with the coal, and the stone material just gets removed on by flights. Pretty inefficient, and if you have an easy type of coal to separate, then they still have their use. For example, in South Africa, you tend to have a lot of material which is called near dense material, which if you have a particular cut point, let's say it's a 1.5 density you need to get the quality, it's the amount of material around that density of 1.5. If you've got very little material around that cut point, then it becomes a lot easier to wash than if you've got a lot of near dense close to it. Then we have various pieces of equipment, dense medium cyclones around at the turn of the last century. The science, I guess, of dense medium pretty much came to the fore with the Stanley Carbon in Holland, putting together the dense medium, what it now called, I guess, the dense medium Bible, which is how to actually be able to control the dense medium circuits with magnetite and water and everything else. So this, as you see, there's more and more equipment available. Things like, for example, filter presses to work on finer material, which is now becoming common worldwide, and things like a reflux, which is a sort of development on a hindered settler, but there's more and more pieces of equipment being used. Some of these are there as, for example, microwave dryer is being tested. I don't know of any particular place where it's actually being used at the moment, but all of these things are available for potential testing. All of these things, a lot of these things are very much on a site-per-site basis, where you look at the actual application and then hopefully apply the right technology for your particular application. Can you go to the next slide, please?
Okay.
Okay, so as Graham said before, the systems that are used to process a miner's 1 millimeter particles are a lot more inefficient than so the minus 1 millimeter particle separation is a lot less efficient than treating the plus 1 millimeter, purely because the settling rates either in water or in a dense medium will be so much faster when you work with coarser particles. One of the biggest challenges with fine coal is the dewatering. It's probably the single biggest effect. The actual heat value of the coal is already there, but some of that heat is actually being used to get rid of the water before you can actually use it as a sensible heat in a boiler or whatever, particularly with thermal coal. Metallurgical coal maybe not as quite so stringent, but still is an issue, particularly when you've got to take the stuff to the market. So you've actually got to make it handleable. So the amount of dewatering that we need to do also site specific. Apologies, and the site specific will tell you how much dewatering we actually need to do. In a lot of cases, the fines and the ultra fines, so they're nominally 1 by 0.2 and minus 0.2 being the ultra fines, can be added to coarser products as long as you don't put too much in, whereas it will then affect the total moisture and the handleability of the coal. So the economics of actually treating fine coal is a balance. We have as Graham said before, if we make just take fines and we throw it away, we could be throwing 20% of our feed away and paying for the privilege of throwing that stuff away. So instantly the maximum yield we can actually get is 80% if we throw 20% of the feed away. So the yield and the quality of the actual fine coal we can make is very important. Let's say we're producing 27 CV for sake of argument, and we can't actually make that product. We can only make, let's say, 24 or 25. We will need to overwash the coarser coal to be able to add back those fines. And obviously, once again, site specific. So the more efficient we can be and the more controllable we can be on the amount of the fine coal product, that will actually make sure that we don't have to overwash on our coarse material as much. Obviously, we also have a cost to the additional equipment, and if we have something like froth flotation, we also have things like reagents that we have to add in, and the quality and the yield of the fine coal, together with by adding it back into the coarser coal, We've also got to calculate the overall revenue. So if the moisture adjusted heat value, the net CVs received, for example, goes down, there will be a trade-off, there will be a decrease in revenue, both in terms of a direct heat versus price, but also a penalty situation when you start getting below certain thresholds. So the economics of treating fine coal is a trade-off, and it's got to be site specific to determine whether it is actually worth treating the fine coal or not. But it's an interesting fact that around the world, that in some cases, some companies and some people, I guess, personalities, will say it is worth treating fine coal. And in some cases, the identical coal, other people will say it isn't worth it, and other people will say it is worth it. And it's sometimes interesting the differences on nominally the same set of economics. That for the same, in one case in South Africa, it's literally the same plant, where one group doesn't think they should actually treat the ultrafine coal, and the other group does feel like they can treat the fine coal economically. Okay, the next slide, please. Okay, so these are the actual different types of equipment for use in miners 1 millimeter separation. You see the top half is effectively the plus 100 type microns, but once again, that's site specific and test specific. As I said before, the spirals are probably the most common type of separator being used. They are cheap, but they are not very controllable. So it's actually, my apologies, so difficult to actually, if you can't make the quality easily, it's not particularly easy to do something to try and get to that quality. The fluidized beds, such as the hindered settlers, which is things like TBSs, refluxes, etc., is more controllable. It's actually a water upflow device, as well as being able to control an apparent density of the bed inside the separator. So you actually have two elements that you can control. Even so, it is, once again, it is water only. So there are circuits which I've used and other people have used, where you actually separate the sizes into, let's say, a plus 0.5 millimeter and a minus 0.5 millimeter, or even better, to actually use the first fluidized bed to really separate out to get rid of the coarse discard, all of the lighter material which will overflow with the water, then goes into a second stage where the minus, let's say, 0.5 millimeter is treated in a much more quiescent sort of basis, so you can get a better separation. Fine coal dense medium is used in a few places, probably not enough. Once again, it's economics. It is more expensive, and it is in terms of OPEX and CAPEX. Although the efficiency is far higher using the fine coal dense medium than it is any other process. So the trade-off has to be made. Water-only cyclone has the same issues as the any water-borne device, and they are being used. There are none in South Africa now because of the higher near-dense material that we have. That so water-only cyclones have basically been pushed out. A fine jig. There was lots of test work over the last on the using fine jigs for miners, call it 2 millimeter material. I know of no installation at the moment. Enhanced gravity concentrators are things like the Nelsons and that type of separator, and the Mosleys and that sort of thing. There is quite a lot of work being done presently on those sort of things. I do not know of any particular full-scale installation at the moment, but there is certainly work being done. Okay, then we go on to conventional flotation using mechanical type devices, where coal flotation chain is different from conventional mineral flotation. For example, let's say you're working on something like a platinum. You might have a residence time of 60 minutes now to give time for the mineral to be separated from the gangue. And your overall recovery on that flotation might be of the order of 1 to 2%. With coal, your residence time tends to be very fast, in the order of 3 to 4 minutes. Once again, textbook will tell you exactly how much. And your recovery could be up to, let's say, 70%. So your overflow from your flotation cell is really critical. So you tend to be, your design of the flotation cell tends to be to increase your lip length to make sure that you can actually remove all your product over the top of the lip. So that's why things like paddles and that sort of stuff are used to actually pull the froth off top of a cell. It also, the influence of a frother type material you make. So the type of frother is important because it makes the froth mobile. A column flotation is really a similar sort of thing, except you allow to wash the froth, so you can actually control the quality a little bit more. Okay, oil agglomeration isn't really being used in many sort of places, mostly because of cost. Okay, can we have the next slide, please? Okay, so on this page we have various types of dewatering. Notice we haven't really, we haven't included drying, thermal drying in this list, and mostly because there are very, very few still going. Number one, they're expensive, and you've got to be able to do the work to see if it is actually worthwhile for you. And the other thing is there is an awful lot of danger involved because you've got fine material, which very easily creates an explosive environment. So we haven't worried about drying at all. So we've got things like high frequency screens. In the old days, they're called something like a phototechnic screen, which will give you, call it a 25% moisture. And then going all the way through to different types of filter press. Belt filters being of higher moisture than you can get using pressure filtration. Any vacuum, by its very nature, can only produce 1 bar of pressure. Goes from 1 down to 0. Whereas if you are using a belt filter press, you can go up to, let's say, 7 bar is routine, 15 bar is possible, so that the belt filter press will actually give you a greater controllability. Filter press will still really only give, if you're dealing with, let's say, a thickener underflow, will which is nominally minus 150 micron, you will only really get about the 20 to 22% at best, I guess. So some of the centrifuge, different types of centrifuges, once again, the test work needs to be done. But things like a screen bowl centrifuge, if you are using a chemical as a collector, for example, where you can form microagglomerates, you are making life easier, and you are making very fine particles which are actually clumping together, covered in oil, which means that your moisture can be reduced. Okay, next, please. Okay, so once we are we're trying to dewater, we must make it suitable for the market. And the dewatering of fine coals, as we said before, is really challenging. I mean, to try and get the the moistures that we need is potentially very expensive, and is also operationally more difficult to do. So we need to do all these trade-offs. But particularly if we are making a product as a standalone type of product, so that it's not being mixed in with any other product, let's say into an export product to go onto a train and to be mixed, we need to be able to make it handleable. And that's where forming of coals, so in other words, making agglomerates or briquettes or whatever, is really important. And it is very important, and it is also very, very difficult. There is some work being, a lot of work being done by various people. Eskim at the moment in South Africa, I did a lot of test work on there, and no doubt that some of that work will come out over time. But the being able to make this a handleable coal is really, really important. But if it was easy to do, everybody would be doing it. And at this moment in time, very, very few people are doing it. There are different types of work being done, but it's on a commercial basis, it's actually very, very rare. Okay, next one, Graham.
Well, I think I can, Peter, I can just take this over for a sec. So,
Thank you.
In terms of the scale of the problem, realistically, we have a table that just estimates this coming up. As we said earlier, somewhere between 10 to 15 to 10 to 20% of the total feed produced is probably reporting down to the fines. And as I said, there's a table to discuss this a little bit later, but there are significant losses to the industry in revenue that has been generated, even using very modest coal pricing compared to what we're seeing at the moment. And associated with the storage of any long-term materials on surface or underground, there's obviously a liability that is associated with them in terms of the responsibility from the environmental perspective. So there are different options for us to store coal, fine coal, both in surface and underground operations. And this is just a very stylized, extremely attractive looking mine, I must say, with some very sharply cut pillars there. But board and pillar mining is one of the underground methods whereby the coal pillar forms the primary support for the roof, and therefore the roof is not intended to collapse, as opposed to total extraction or longwall mining. And the board, which is the roadway in between, the coal is removed. This process generally allows you to extract between about 50 and 70% of the coal. As you go deeper, the coal pillars become bigger to allow bigger support, and therefore you extract less coal. So it's not often used much below about 100 meters of depth, depending on the thickness of the seam. And potentially, and it happens quite a bit in South Africa, is that the slurry or slimes can be pumped underground into the oil workings and left there, and in some cases can be recovered afterwards. There has been over the years situations where companies have gone back in to mine both the coal pillar itself, because the quality of the coal tends to be quite good, and the slimes themselves. So that's one option for us. On surface, it's obviously stored in settlement ponds or settlement dams, but there has been significant issues in some countries in the past, and some of you may remember a particularly devastating situation in Wales in 1966, when a waste dump, not a pure coal dump, but a waste dump including coal, mobilized during a heavy rainfall period and destroyed a school with very, very significant loss of life. And also in the USA, particularly in Kentucky, there have been several dam failures, which generally speaking have not caused a human loss, but have caused significant environmental damage to rivers. And so there is a long list of issues that have originated from both waste dumped with coal mixed in, the fine coal mixed in, or fine coals themselves. In studies in Kentucky and particularly in Poland, waste dumps themselves can self-heat quite easily, usually caused because of the pyrite content within the material, to cause a reaction which then leads to burning, which then of course creates all sorts of ash and airborne problems. as well as carbon dioxide levels as well. So storage can occur in two different ways, as I say, on underground and on surface. But although the underground one can generally be a little bit better from an environmental point of view, neither are ideal. And this, excuse me, this is just an example. You should be able to see at the bottom of the screen. This is an area of the WITBANK coalfield in South Africa, one of the prime export areas of coal, although it does supply domestic power stations as well. And this is roughly about 50 kilometers by 40 kilometers, just to the south of the towns of WITBANK and Middelburg. And this was just really to highlight the number of both dumps, which will in some cases have fine coal. So some of these are the names of the mines. Bank Dump is one of the mines now belonging to Tugela, as is Huruhup. Interestingly, in the bottom left-hand corner, you'll see a mine, a name there, Reedspread. Reedspread actually concluded or stopped coal mining in 2001, but has not yet had environmental sign-off, mainly because the slimes dams are still there, and the original box cuts, the original first cut of the open cast, where the the first kind of hole is dug to allow access to the mine, have been filled up with waste material and fine coal, and that is causing environmental issues, which mean that has still not been signed off and remains an ongoing liability for the companies that own it 20 years after production actually ceased. Peter will just take us through quickly a very conceptual sort of financial analysis, and we stress that just to show the different options that there are. But every coal is different, every dump or every slimes dam is different, depending on whether it's perhaps a very old one and the logistics have been removed, or whether you're operating on an operating mine, which would still give you access to the various logistical options to remove the material, the product to the market. So there's huge amounts of differences, but Peter will just run through it. I'll just point out that we're using a figure here of $75 a ton as a typical example, and that's purely because, as I'm sure most of you are aware, the coal price is way above that, but in levels, in sort of stratospheric levels that I've never seen in the industry, and it's very difficult to know where the longer term price is. The World Bank is still suggesting a return to about $80 to $85 a ton in the next 18 months to 2 years, and I think most of us feel that has to be some sort of return to that sort of level. Personally, if I was starting up a mine or starting up a treatment process for fine coal, I'd want to be able to be producing it, certainly for the export market, at about $50 a ton or less, to give you the margin that if the coal price does revert back to what is generally considered a long-term medium, you're going to be looking at a profit at about $75. So, it's almost pick a number at the moment with the coal price where it is, but we just thought we'd put these up, and perhaps Peter, if you could just run through the different options.
Okay, so what I've basically put in here is, so some of the words are slightly wrong at the top of the slide. I should have actually checked those, my apologies. Basically what I've done, everything's site specific, as we said before, but what I've basically said here, the first column, my apologies. So the first column, we had a sort of base case where no fines and no slimes were treated at all, and these are over and above that. And like I said, my apologies today. These are slightly wrong, but we've got what I've got on here. Basically, the first column should be no flotation. And we use spirals for the fines, okay? And then we dewater the fines in a simple device like a phototechnic screen at about 25% moisture. Over just throwing everything away, not including any dumping costs, we would then, on this fictitious operation running at about 500 tons an hour, we could make an additional $10.4 million per annum, which is about a 5-ish% increase differential revenue using very basic technologies, spirals and phototechnic screens, a dewatering screen. And because it's very cheap, the payback is also very quick, less than a month. The next one, once again, it should read, once again, my apologies. The next one should be no flotation. We are using spirals of fines, and we are using a like a screwball centrifuge. The increase in revenue and cost is actually quite considerable because more sophisticated centrifuges are a lot more expensive. But the overall revenue is of the order of a 9% increase over the base case by increasing the dewatering technology. The third case there, once again, my apologies, is no flotation of spirals. But what we will use is actually something like a TBS, or hindered settling device. And what that will do over the efficiency of a spiral is you would get increase of yield. So your yield will be about the same, but your CV, your heat value, would increase in most cases because of the increase in efficiency and because of the controllability. So yield of the fines is about the same, but your CV has increased, which means your revenue loss because on a dewatered on a heat adjusted basis increases. Once again, it's slightly more expensive, so we would be looking at a higher capex, but our payback would be that our revenue would be a lot higher. Okay, and then the last two we have, we do float the slimes. We also use spirals for dewatering, TBS for treatment of the fines, and we have flotation of the slimes, and we have screen bowl centrifuges. So in that last case, we are basically from left to right, we're increasing the amount of technology that we're trying to apply to the process. Once again, everything's site specific, but we are trying to increase the technology. So we're going from just dump on the base case, putting in just spirals with the dewatering screen. Then we're looking at putting a screen bowl centrifuge. Then we're looking at flotation of the minus 150 micron material. And we're looking at putting in TBS or the hindered settlers on the fines as well instead of the spirals. And in the last case, we have hindered settlers, plus we have flotation, plus we have screen bowl centrifuge. So it is more expensive, so our capex has gone up to the heady heights of just over 4 months payback. But our increase over the base case has increased by about 14%. Now, one of the things I guess when you're doing a project like this, and you're coming up with numbers like this, which are not, once again, site specific, but it's certainly not uncommon to have numbers like this, is why isn't it being done more often? And I guess that's the number one feedback from this project is potentially it should be done a lot more. Okay, Graham, we will check update this slide before it's actually given out. My apologies.
Okay, so just finally, we just providing a quick review of where the sorts of levels of fine coal being produced is, particularly regarding exported countries for coal. So essentially, the countries that primarily wash most of their exports and that therefore produces most of the fine material are Australia, South Africa, Russia, and the US, although less so in recent times. Now, significant amounts of coal tonnages are treated in China and less so in India for the domestic market, but in very different circumstances and with very different types of plant designs. So it's very hard to know exactly, what levels of those are being produced. So we tended to focus on the countries that we know a little bit more about. And in general, the treatment of fine coals is still relatively rare. This is just an estimate that is quite theoretical, but just to give it a flavour of where we think the numbers might be. And it suggests that we're somewhere in terms of production from these main countries, probably looking at about 100 million tons of material per year, which relatively small volumes, mainly in Australia, are actually treated, but most of it probably isn't. And if you think that that situation has probably existed for at least the last 30 years, or certainly most of Peter and I have been in the industry now for about 40 years, and really most of that time fine coal has not been treated. You're probably looking at an overall volume of somewhere between 1.5 and 3 billion tons of material is still sitting in some sort of storage facilities, largely untreated. So what are the main companies that are doing it? Well, Circ in Russia have installed flotation cells on one mine where they were dumping about 1 million tons a year of fine coal. That was being actually dumped into the spoils, the opencast residue, so that was pretty much lost forever. In South Africa, Tungela are treating some fine coal and on certain number of their mines, and Glencore certainly operate flotation cells, which are the primary methodology being used in Australia, and their technology site lists about 150 flotation cells being used globally, with most of those being in Australia. However, it's important to know that some of those, the volumes that those flotation cells can usually produce varies widely. So although one mine may have 6 flotation cells and another one may have 2, the overall volumes being treated may in fact be quite similar. So what we can say is that treatment of this material outside Australia is pretty rare, and where they do it, it tends to be that to overcome the problems of pelletization, the material is trickle fed back into the operations. Now, 1 or 2 companies around the world are beginning to look at treating older materials, opposed to those mines that I just referred, or those companies I just referred to, that are dealing with material that they're still producing themselves. So ARC are a company looking at, or have constructed largely, 100,000 ton per year facility in Kentucky, where they're treating old slimes dams to actually create a very almost pure carbon product for use in bunker fuels. Company in Poland is looking at processing coking coal redumps with a content of about 20% coal. Company in England, in UK, did try to produce, or did work for a while, treating thermal coal dumps and reshaping the material that was left back into a more sort of acceptable profile, but really struggled a few years ago as the market declined and the prices were poor, and have since ceased trading. And in Mozambique, the Moatize mine is looking to treat a significant number of fines, residues that are there. Now, as Peter said, part of the trick here is that if you want to produce a material from fine coal which is acceptable and can be transported, you really have to look at creating some, dewatering it and producing some sort of pellet or briquette. And this sort of technology has been around pretty much as long as Peter and I have, which is, you know, pretty scary to think it's getting on a combined period of a century, but anyway. And nobody has really come up with technology which really commercially has the volume capacity to really, you know, produce the right sort of materials. And bear in mind that for most mines, in a very rough rule of thumb, you want to be able to process about 1 million tons a year to make it sort of worthwhile. It's not much good having a facility that can produce perhaps 10 or 15 or 20,000 tons. It doesn't create enough revenue generation to warrant itself. So we know in Australia, these are nearly all very small companies. Alios have a small pilot facility. Changeover Technologies do in the UK, in Northern Ireland actually. And the STEC is also in Australia, I think, is also looking at preliminary tests. And I'm aware of a company in the UK called Grinding Solutions that have done successful bench tests, but not gone past that. And another company in Australia has been looking at dewatering it over adding chemicals that do it, but it tends to be time consuming and relatively expensive. At the moment, Peter is working with the university in South Africa, not on pelletization, but using recyclable ceramic balls to potentially dewater the product. That looks encouraging, but again, it's really at a lab stage, so there's nothing on a commercial stage that we're aware of. So in summary, the fine coal treatment does represent a financial opportunity. It does also potentially avoid an environmental problem if you can do it at the same time as you're mining the coal. But the problems that really exist in terms of becoming commercial in these areas revolve around the large-scale treatment of a fine coal and then putting it into a format or a method that allows you to actually transport the material. That means a pellet which is robust enough to stand up, but going through the various handling processes it'll have to endure as it leaves the mine and goes to the final product, and also getting the water levels, the moisture levels down to levels that are believed to be consistent. So there is a huge opportunity in removing many of these dumps that exist, both waste dumps with fine coal in them and fine coal dumps, slurry dumps themselves. We see that the technology is being advanced, but it's generally speaking being advanced by relatively small companies, and as yet we're not aware of any of the major product producers that have really grasped this and have taken it on. So we'll see how the future moves forward, and thanks very much. I've just got a couple of questions here. Hang on, I'm just looking at them now. The first one is about how the potential use of fine coal. Well, you've really got two options on what you can do with it, as we said. One is if you can produce a satisfactory quality, you can trickle feed it. In other words, put a very small volume into your main product, and most customers will accept that. The second is you have to find if you can't do that, you have to find a way to dewater it and to either pelletize or briquette it in a way that a customer will find acceptable. And the big problem with briquetting and pelletization is usually revolved around getting to a commercial scale with a binder. Some methods use a binder, and there are up to 50 different types being used, including starch and oil or all sorts of different things. Or ideally, and that's got to have a zero impact on the way the coal is being used. And also some companies are looking at just using pressure, so a binderless technology, but nobody has really come through with it on a commercial scale. So that will be the primary usage for the types of coal. And another question is, has work been done on the combustion systems that fire a coal slurry and recover heat from evaporated water? I'm not aware of it. I'm not sure if Peter has, but again, it tends to be finding enough material to deal, to make a plant which is commercial, and recovering heat from the evaporated water would tend to depend on the location of the facility. And for example, in Australia, where a lot of this coal, or South Africa, it doesn't tend to be such a major attractive market. Could it be of interest? Yes, it could. And I think we are moving into a world now where we have to think differently and look at different opportunities. So it's one that I think should look at potential opportunities for all sorts of usage of fine coal. Another question is regarding the binders. In the report which will follow this, there is a detailed review of the different binders, and Peter can perhaps comment, but people have looked at starch, they've looked at sort of oil type products. As I say, some of the best ones are really ones where you don't have a binder, because it would be the most effective. Some have used clay in the past, but to our knowledge, none of them, because the binder itself tends to obviously create a cost. You've got to also find a source of the supply of the material. Is being quite difficult to actually, so a wide range of binders has been used, but I think personally the way forward would be to try and get into a pressure situation whereby you don't have to use a binder at all. And there's a final question. What should be the particle size distribution of the coal fines in the slurry suitable for dewatering? Well, Peter, you might want to just comment on the particle size related to dewatering. I'm assuming the smaller the size, the more dewatering issues you're going to deal with.
Yeah, I mean the smaller the particle size distribution overall, the bigger the problem. You can effectively dewater down to pretty much zero, but obviously that it's more and more difficult. There are situations where people, if you take a feed to flotation, there are quite a few places where they actually try and remove of the order of 30 to 40 micron material and don't put that in the flotation. And it's got two reasons for that. Number one is because of the massive decrease in surface area because of the fineness of the particle, you will use an awful lot less reagents, and for the same reason that the lower surface area, is much easier to actually dewater that product. So basically the answer is you can go down to zero, but you need to be fairly site specific and do the test work to see what is your best option for your particular type of coal.
Okay, so that was quite a long session. Apologies for that. I think, though, Benedicte, that's all the questions answered now.
Yeah, brilliant. Thank you so much. All that's left for me to say is these slides from the webinar will be available from the webinar page of our website a bit later today. And thank you so much, both Graham and Peter. Thank you all for joining us today, and goodbye.
Thank you.